Hi, I'm Dr. T, and welcome to my office. So let's talk about functional groups. So when we're talking about organic chemistry, we often want to start understanding what the molecules do and how they behave, and this is actually quite often easiest and most effectively done by looking at the different parts of organic molecules. So if we have the most basic organic molecule, this would be a straight hydrocarbon, or branch potentially, because you can have either carbons in a straight line or they can do some weird squiggles and have forks and whatnot. These hydrocarbons are going to be fairly chemically inert. If you heat them up enough with some oxygen, they will burn, which actually is a great source of energy. They're a wonderful fuel. Of course, they do produce carbon dioxide, and there are some downsides to burning these things, but as far as energy density goes, there's a reason this is the dominant fuel source that we use. They make a good fuel. But otherwise, they don't really do too much chemistry. They don't tend to react with things, which is also why we use them for lubes and protective coatings. They typically don't interact well with water, so okay, they keep water off too. Great for a protective coating. Your basic hydrocarbons are actually really helpful molecules. They're very, very useful because they don't do a lot except for at high temperatures they do burn very nicely, which is a useful thing to do as well. But adding things onto them to give them other properties is what we refer to as functional groups, or I should say the things added onto them that impart other properties are known as functional groups. So in this case, we can start looking at our molecule and seeing what different things we can do. The simplest functional groups are double and triple bonds. So typically, carbons bond to each other by sharing a pair of electrons. They, however, can share 2 or 3 pairs of electrons. The way the second and third pair of electrons are shared is slightly different, and this does impart some interesting chemistry, allowing them to be a little bit more chemically reactive and doing some rather interesting things. These are sometimes referred to as elements of unsaturation. If you're thinking, hey, like an unsaturated fatty acid or unsaturated fats like olive oil? Yes, exactly. Those have double bonds in them, and that's partially why they're a little bit runnier than their saturated cousins. Double bonds create a kink in the chain that makes it harder for them to become a solid, but also is why they typically have a somewhat shorter shelf life. The double bonds are more reactive at normal temperatures to things like oxygen or other random stuff. As far as these go, they're quite often useful as chemical precursors. Ethene, which is 2 carbons with a double bond and each one having a pair of hydrogens, is a classic chemical precursor and is used heavily in the chemical industry. That double bond allows it to form other things, and hey, it's great if you got something small you can stitch together into other useful things. Now, we can do something rather interesting with double bonds, and that is if you have a ring, and rings do exist, but they're not overly common, and if you alternate the double bonds in that ring, it does change the properties actually quite a bit. The alternating double bonds within the ring allow the electrons to be shared between the carbons, something that we normally don't think of nonmetals doing. But if you attach a bunch of these rings together, you get graphite, which of course is pencil lead and also conducts electricity. Yeah, your pencil lead does conduct electricity, even though there's no actual lead involved. Weird. Yeah. Next other feature to these guys, we call them aromatic because quite often, with a few other functional groups, they will have interesting smells. The downside of aromatics is that, especially when they're small and don't have other interesting functional groups on them, well, your DNA also contains aromatics, and they can interact with your DNA in ways that causes cells to make oopses. And an oops in the DNA is a great way to make the cell go rogue. And by rogue, I mean cancerous. So aromatics, if you've got other functional groups on them to make it so that they don't decide to go wedge themselves into DNA, great. Let's talk oxygen. When it comes to oxygen, this is one of our quintessential atoms to add into our hydrocarbon to give us some interesting functional groups that will make life more interesting. So the quintessential oxygen functional group is the alcohol. In this case, we wedge an oxygen in between a carbon and a hydrogen, and all kinds of interesting things happen. So in this case, whereas the hydrocarbon itself, the carbon and the hydrogens, don't particularly have any uneven sharing of electrons. They share nice and evenly. And therefore, their attractions between different molecules are not nearly as strong. That oxygen, yeah, it hogs the electrons, and because of this, it creates a partial negative charge on the oxygen and a partial positive charge on the hydrogen as well as the carbon, but more so on that hydrogen. This has a couple of consequences. Because this is what we call polar, the partial negatives and partial positives will attract to each other of different atoms, and therefore they tend to stick together. So alcohols will be a liquid where other hydrocarbons of similar size would be a gas, or even the alcohol might be a solid compared to a gas or a liquid. Additionally, water has this same polarity to it, and thus, because both are polar, they tend to mix much better together. So whereas most hydrocarbons that don't have interesting functional groups typically don't interact with water, alcohol functional groups will get hydrocarbons to interact with water fairly straightforwardly. Now, oxygen doesn't have to be wedged in between a carbon and a hydrogen. It can do a couple of other approaches. It could be wedged between two carbons. This is an ether. They basically have similar properties to the hydrocarbon. They do tend to stick to each other a little bit more, but nowhere near as much as that of the alcohol, because that hydrogen was easy to steal the electrons from. Now, oxygens can form two bonds, and they can be to the same element. So we could have an oxygen forming two bonds to a carbon. This is what we know as a carbonyl. And this can come in a couple of different approaches. So we can have a carbonyl where the carbon is attached exclusively to other carbons. This is a ketone. Or we can have a carbonyl where the carbon is attached to at least one other hydrogen. This is called an aldehyde. The aldehydes are somewhat interesting is because both the ketone and the aldehyde are fairly chemically reactive. The aldehyde is actually a good deal more chemically reactive. Turns out that hydrogen being so small allows for more chemistry to take place. Typically speaking, aldehydes tend to be a tad bit on the toxic side because of this enhanced chemical reactivity. Interestingly enough, glucose, yes, blood sugar, is an aldehyde. The origin of why diabetes is a problem. Too much glucose, too much aldehyde, too much random damage being done to blood vessels. Yeah, I'm not going to say yeah on that one. That's just lousy. Now, we can do a couple other things with oxygen. We can start combining functional groups together. A carbonyl attached to an alcohol is what we call a carboxylic acid. Turns out the two oxygens are able to hog the electron enough that the hydrogen will sometimes pop off, forming an acid. If that hydrogen isn't there, so it's carbonyl and an ester, and an ether together, we get ourselves an ester, which is an interesting linking functional group, which we will talk more about when we talk about the wonderful world of polymers. A alcohol on a aromatic ring is known as a phenol, which is interesting enough because it does somewhat different chemistry. The electrons can all hang out between the 6 carbons of the aromatic ring and the oxygen, and thus slightly more interesting things take place. Phenol is the classic disinfectant. Oxygen, of course, is not the only atom out there. Nitrogen can join in the party. Nitrogens attaching to carbons is known as an amine. These can occasionally become bases or able of accepting hydrogen pluses, which, is sometimes a absolutely critical part. See more when we talk about biochemistry. Additionally, they do tend to have a bit of a bitter flavor, which can be removed by adding a bit of acid. These are why things like spinach are bitter, amines, as well as other nitrogen-containing compounds. Interestingly enough, this is also one of the reasons why people typically don't like bitter foods. A lot of psychoactive, or a lot of pharmacologically relevant, I should say, compounds contain nitrogen, and they also tend to be a bit on the alkaline side, or basic. Thus, as a way of avoiding them, we typically don't like bitter foods, although those are an acquired taste because sometimes you don't want to avoid those psychoactive compounds. I'm talking about caffeine here, not something else. That said, have a wonderful day.